Greetings, everyone. Welcome to Organic Chemistry 2, concluding our discussion of amines. We skipped this section when we were finishing up last lecture. We talked about the basicity of amines a little ahead of time, but that does not matter. They're all important topics. Here, we're going to review the alkylation of ammonia. Previously, we already discussed that it was not a good idea to try to make this molecule by reacting ammonia with butyl bromide, because you will only get a small yield of this molecule as it further reacts as a nucleophilic amine, just like ammonia reacted like a nucleophile here. This amine is an equally good nucleophile, and it will attack a second molecule of butyl bromide, neutralization. Please note here, there's two butyls on here. I short formed one of them to Bu, and neutralization yields a secondary amine, which is also a good nucleophile. And there's two butyls here. There's about to be three as we put in a third mole of butyl bromide, and we neutralize our butyl ammonium ion to get this species here with three butyls on it, two butyls, three butyls, and a neutral amine after neutralization. And yes, the lone pair is back, and a tertiary amine is also a nucleophile. And yes, a fourth reaction occurs. So why did I just spend all of this time discussing this when I just said this is not a good way to make a primary amine or a secondary amine or a tertiary amine? Not good for any of them. You get the old proverbial dog's breakfast here, mixture of many things. Well, if we do employ our knowledge of Le Chatelier's principle, saying that if we have a huge excess of one of the molecules, we can push this thing to this conclusion right here by having a large excess of butyl bromide. And then we're going to learn very shortly that these ammonium salts are in and of themselves very useful molecules. Then we do see a useful procedure for making quaternary ammonium salts. That's what this procedure is good for, making quaternary. I'm trying to get my pen to work here, and there we go, finally. It doesn't look nice. Quaternary ammonium salts right there. So the only way to have a high yield of any of the products is to use a large excess of butyl bromide right here. And then you're going to drive this whole sequence to the end, and you end up with a very good yield of your quaternary ammonium salt. And what good are quaternary ammonium salts, you ask? Well, here's two very common ones. You'll see this kind of a label on a lot of things. Ranges outside of household products, bactericides. I think I've seen something in insecticides somewhere with this name benzalkonium chloride. And the reason they're not very specific about the alkonium is sometimes they vary the length of this chain here. Here it's a decyl group, isn't it? But it's in the broad category of benzylalkonium chlorides, and it's a preservative. Bacteria hate these things. It kills bacteria, that's why. So we put them in hand sanitizers. Your soft soaps often have these, and these act like soaps. In fact, they are called invert soaps. Invert soaps is another name for these quaternary ammonium salts. My pen's doing funny things on the screen. I don't know if you see it. We're getting shadows. Okay. Invert soaps. What makes them invert soaps? Well, if you recall a traditional soap, I will sketch one real quickly over here. Stearate ion was a good soap. Stearate has a carboxylate over here. Carbonyl, 2, 4, 6, 8, 10, 12, 14, 16, yes, 18. Stearate is octadecanoate, the conjugate base of octadecanoic acid. And why was it a soap? Well, it was a soap because it had a nice hydrophilic polar end here. Hydrophilic, loves water. And we had a hydrophobic portion down here. Hydrophobic. So it, okay. And all of it's gone. Hydrophobic end over here. And it is attracted to things like grease over here and gets washed away over here. I think you remember the expression micelle from our previous lectures when we studied derivatives of carboxylic acids. It forms micelles, which are spherical, and these are in the interior, and they attract grease. Well, invert soaps have the same properties in that they have a hydrophilic ion. So hydrophilic ion portion right here. And all the rest of the organic stuff is hydrophobic. I really shouldn't circle the chlorine though, should I? There we go, the chloride. There we go, that's hydrophobic. So this end will stick its nose in the water, and the tail, the hydrophobic tails, will either associate with each other or stay out of the water. Invert, where'd that word come from? Well, what was the charge on the hydrophilic end here? Negative. What's the charge on the hydrophilic end here? Positive. The charge has been inverted. There you have it. And then here's another invert soap that we're going to actually look at how it does what's called phase transfer catalysis down on the bottom of the page. Phase transfer catalyst right here. And what does it do? It does what it says. It's going to be a catalyst that takes a species from one phase of a reaction to another. And this one's called Stark's catalyst. I'm never going to ask that guy's name. I only learned it a couple years ago myself. And I have to admit, I've been using the catalyst for 20 years. Confession. All right, it's got 3 octyl groups and a methyl group. And it's an ammonium ion because it has 4 R groups. And its trade name is Aliquot 336. That should ring a bell to some of my lab students who used it in the lab. And this is the lab reaction down here. It was part of the Horner-Wadsworth-Emmons-Arbuzov protocol. And most books don't give Arbuzov any credit at all. I don't know what's happening here. Horner-Wadsworth-Emmons-Arbuzov protocol says we have to take a phosphonate and take its proton off. Well, we have an issue right there. We need a fairly strong base. It has to be ionic. None of our other bases are strong enough to take a proton off this alpha position. This is alpha to a phosphonyl, so we can still call it alpha. You want to review, since review is the order of the day until the end of the semester. pKa 20. My pen is giving me conniptions today. 20. And we need a fairly strong base to grab that. Hydroxide, not quite strong enough. So if you remember when we looked at this lecture earlier, we used a huge excess, as we did in lab as well, to force that equilibrium. But you don't get any reaction at all unless these two can meet. Right now, here's the situation. I've added all the ingredients I need. I have my hydroxide somewhere. Oh, there it is. It's in the water layer. We have two layers here, two phases. Two phases. We have a water phase and we have an organic phase. In this case, we use hexane. Why is it on top? Well, it has a lower density than water. That's why it's on top. Well, hydroxide's stuck in my water phase because that's where it dissolves, and my phosphonate ester is up here. It does not like water at all. It's not very polar. So how is the hydroxide going to react with it if it never sees it? Well, that's where the phase transfer catalyst comes in, isn't it? Phase transfer catalyst is sitting here, like I said it would be, with its nose sticking into the water with the ion, and its tail in the less polar hexane solvent. And hydroxide sees that ion poking its nose down there and is attracted to it, so it wanders over. This is not a mechanism arrow, it's a wandering over arrow. Look, it's now nice and close. So the anion and cation are more balanced now. So a little less charged. Now this can push the hydroxide up to the organic layer, and then the hydroxide meets the alpha hydrogen of the phosphonate ester, and it does what bases do. It takes the proton, and you have a carbanion, which can undergo the Horner-Wadsworth-Emmons-Arbuzov reaction with an aldehyde or a ketone, which has been lurking here all along, not doing anything. Benzaldehyde will react, and if you were curious, here's the reaction. This is the Horner-Wadsworth-Emmons portion of the proceedings right here. And this was the Arbuzov reagent over here. Let's give him credit where his name should be. And we get a Wittig type reaction, although this one favors the more thermodynamically stable transalkene, and the Wittig favors the kinetic product, which is the cis. Unrelated to this conversation. So where do we stand right now? We stand at a very short segment, but we do stand with the conclusion of chapter 23. So that is it for all of the test material. No new stuff until after the test, and the test is next Wednesday. And we've had requests for review items already. We had a kind request for the aromatic questions in part 1, which you're going to have at least, well, you're going to have half of these. Not these specific questions. You know how that game works. It's all new molecules, every test, every time. Okay, so aromatic molecules. Do you remember the rules? Should we review the rules while we're here? That's what review's for, right? We have to have the right number of pi electrons. 4n plus 2 pi electrons, pi. Thought I was typing and I was going to change the font. It reminds me of during a test, I saw a student with a big old eraser on their desk and it had the word edit written on it. I thought that was very clever. Sorry. 2. Must be cyclic. And 3. All atoms in cycle I'm going to paraphrase the actual rule. Must be able to resonate. And if you remember, the only things that can resonate, the only orbital that can resonate is a p orbital. So the only hybridizations that have p orbitals left over are sp2 and sp. And do you remember that even if you have a lone pair that normally wants to live in a hybrid orbital, that you can rehybridize that rather easily into a p orbital so that you can do this number 3 if that lone pair is necessary for resonance. And you just have to ask yourself, do I need the lone pair for resonance? I'll skip to E since we're on the subject. Each nitrogen has a lone pair. I am not going to use this lone pair for resonance in the ring because I'm already using this pi bond for resonance in the ring. So you can't use two sets of p electrons from the same atom. They have to resonate with only one orbital at a time. So I'm not going to use the blue there. I'm not going to use the blue here for the same reason. I am going to use the green for go. That nitrogen is, without rehybridizing, cannot resonate. So it rehybridizes, puts the lone pair into a p orbital. If it's in a p orbital, it can be counted with the other pi's. Now you have 2 plus 4 because I have 2 pi bonds already showing. And we have a winner for being able to resonate. Now in this one, you have 2 4 pi electrons here. These pi electrons are not available. They are making pi outside the ring. These are making pi outside the ring. And you can't resonate in a circle here. You can only resonate to outside the ring. So I got a few things wrong with this thing. And I'm just going to put a big X on it. This is good old benzene. It can resonate around, as is this one, and as is this one. So you'd do A, B, C, E as your answer here. B, C, E. E. That's my answer. Now we had ions that could resonate or not, depending on the situation. If this was not a cation, this thing would not be aromatic because it would be sp3. But now it's a cation, it's sp2. It means it has a p orbital. Sure, it's empty, but it's available for resonance. If we have the right number of pi electrons, 2, 4, 6, we do. All the criteria are met there. This thing doesn't bring any pi electrons into the game, so the number 4 doesn't work here. Oh, I should explain why each one. This one can't resonate in a circle. Resonate in a circle. So I guess maybe I should modify my statement number 3. All atoms in cycle must be able to resonate in a circle. There we go. Got an extra dot now. Haven't saved in a while. Here we go. What about this guy? 2 pi electrons. That works. Even had a student telling me about this in a lab. Apparently, they found a cation like this in the atmosphere of some planet. I didn't check into it, so I can't verify that, but it's a pretty cool story. It has 2 pi electrons. That fits 4n plus 2 when n equals 0. 4 times 0 plus 2 equals 2. And we have 2 pi electrons right there. This is sp2, which means it can resonate with a p orbital. And these guys are already using p orbitals, so they're able to resonate. And this one, well, you could say, all right, there's a lone pair there. I'm not going to use it because it would give me I couldn't solve this with an integer. All right, now you say if you didn't use this, then it has to stay in a hybrid orbital, and that means that carbon can't resonate because you don't have an empty p orbital or a p orbital with electrons in it. You put those pi electrons into a p orbital, now they got to count towards the circle resonance, and it's the wrong number. So depending on your approach, it's wrong on a couple levels. You can stick with the old 4n plus 2. 4n plus 2 equals 4 is not going to be solved with an integer, is it? 4 times 4n plus 2 equals 4. Let's see, what's 4 times 1/2? It's 2 plus 2 equals 4. And that's not good because half. I got pen issues today. I'm really sorry. Not integer. And it's got a pair of electrons here too. And if you use those, you get the right number. You get to 6. That's good. And you have to rehybridize the lone pair into a p orbital, which is good. Everything's working there. And we actually use that anion in one of our labs in Orgo 1 lab at the end of the semester. So some of you will get to see it either in real or virtually. And we're going to see that A, C, and E should be the right answer here. A, C, E. And now we have this guy, which is one of those, what do you call those? What do you call those? I'm trying to remember myself. Large ring aromatics are called annulenes. And this one, you want to know its name? Sure you do. 2, 4, 6, 8, 10, 12, 14, 16, 18 annulene. Does that fit the number of pi electrons being aromatic? What's 4 times 4 plus 2? N equals 4. Check. Now, before you go around checking the number of pi electrons here, I want to point out that in the middle of this molecule, there's an H right here, and it wants to stick straight down. On the carbon right below it, there's an H that wants to stick straight up. They're right on top of each other, which is physically, okay, how I got erased there, I don't know. Physically impossible. My pen issues are going to get me today. That's an H. H on top of H, physically impossible. And that's one of the rules I didn't even cover, but it's now, apparently it's important. I covered them during lecture. I just didn't encounter them until now. 4. You can't resonate with other p orbitals unless you're lined up with them. You can't line up p orbitals unless the molecule starts flat. And this one physically can't be flat. Not FLAT. Got that line in there, didn't I? Okay, so no. I think this was one of the ones that I hinted was my favorite. Let's make sure we have the right number of pi electrons. 2, 4, 6, 8, 10, 12, 14, n equals 3. 4 times 3 plus 2 is 14. Check. And yeah, everything's sp2, every single atom. And we can definitely resonate all the way around here. We can resonate up around here and then resonate around here. Do about 14 resonance forms there. And check. What about this guy? He looks strange. 2, 4, 6, 8, 10, 12, 14. Looks good so far. Oh, there's this little trick on this one. I almost tricked myself too. I was starting to think, sure, why not? That's an sp3 carbon. You can't resonate through this carbon. It's not aromatic. Now you could argue, and that's a decent argument. This question, when you encounter it on the test multiple times, I'm talking about the whole molecule being organic, okay? So yeah, you could argue, hey, this portion's aromatic right here, so it's aromatic. This little ring can resonate with 2 nice resonance forms. You know I'm not asking that. I'm asking are all the rings linked together aromatic? And we got sp3. in the rings that can't rehybridize. So rule 3 is violated right here. All atoms in cycle must be able to resonate in a circle. That's not happening here. And here, let's count the pi electrons. 2, 4, 6. Let's stay on the top. 8, 10, 12, 14, 16, 18. That's n equals 4. I'm leaning towards yes so far. And I'm not seeing any sp3s that would change my mind. These don't have to worry about H's on top of each other. These are bonds. It's good to go. I like it. Looks like ACE was a winner that day. Every answer's had A, C, and E. Which molecules below are aromatic? Same story. This one looks very strange again. But let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18 if you use the lone pair, which you would have to. And which means this one's not going to work at all. And so I'm liking this one and not liking this one. Oh, I already have a check mark. 2, 4, 6, 8. And yeah, it's sp2, but you got 8 pi electrons. Boron doesn't have lone pairs. That's not its nature. Unlike nitrogen and this carbon anion, which I'm liking. C's finally taking the day off. And we've got ADE. And there you go. And we'll do a quick little preview, unless we have a question based on this early review. We'll do a quick preview of our next question, and then we'll start that question after our first break. And you guys can email me further requests. That's why I'm going to show you what I have so far, so we don't have to waste your time. So what we have is requests from the textbook. I was happy to receive this, where we're supposed to give the products of the following reactions and indicate major and minor if there's more than one formed. We had a request for H and J, although I really want to do I. The student may have wanted me to do I. The short form was H/J, which could read H through J if you read it one way. So we'll do HI and J. And they also wanted some mechanisms done. So we're going to do mechanisms for each reaction below, indicate the major product where necessary. And I believe those 2 items will definitely take our whole second segment. So we'll do the first 3 right here on the page. Go straight down. And I'll see you after the break. Adios.